All right, now let's go into some examples. So example 1, from 1910 to 1919, the batting averages of Major League Baseball players was approximately normal. And they give the mean and standard deviation. Can you construct a sampling distribution of the mean batting average, so the mean batting average, for random samples of 15 players? What would be the resulting shape, center, and spread? Well, to me it helps by, just like that simulation, it had the population sort of up here and the sampling distribution down here. What I like to do is draw the population and the SDOM just to give myself a sense of what's going on. So the batting average is approximately normal with a mean of 0.266 and a standard deviation. So the standard deviation of 0.037, right? So the mu is 0.266 and standard deviation is 0.037. What is the resulting shape, center, and spread of the sampling distribution of the mean batting average for random samples of 15 players? So we know from the central limit theorem that it should be, it's a terrible normal distribution. It's not even a good line. Okay. So we know that whatever this is, this should probably be skinnier, but it should be approximately normal, right? So n is 15 because we're using little n because it's the size of our samples, right? So it's the sample size. We would use big N sub x bar if we were talking about the number of simulations that we had done, but we're not doing any simulations. What would be the resulting shape? Well, I would say approximately normal, right? What would be the center, right? So that's mu sub x bar. And we know that mu sub x bar equals mu. And so that equals 0.266, right? So there we have center. And what about spread? Spread would be the standard deviation of the SDOM, right? So sigma sub x bar. And we know that sigma sub x bar is equal to sigma divided by the square root of n. And so that's 0.037 over the square root 15, square root of 15. I'm just going to pull up an Excel file in order to do my calculations. Feel free to use a calculator. Divided by the square root of 15. And we get 0.009, we'll say 6. 0.0096. And so we see that this is much smaller than this, so it's a skinnier shape. So skinnier spread, so not as much spread. And so there you have it. We have the shape, center, and spread. Example 2. Consider the sampling distribution of the mean, so I like to think, SDOM, of a random sample of size n taken from a population of size big N with a mean of mu and a standard deviation of sigma. For a fixed n, how does the mean of the sampling distribution change as n increases? For a fixed n, how does the standard error change as n increases? Well, whether n increases or not, mu sub x bar equals mu. So n doesn't matter very much, right? That's one of the things we saw. For a fixed big N, how does the standard error change as n increases? Well, we know that sigma sub x bar, the standard error, is sort of inversely proportional to the square root of n, and the standard deviation of the population, right? So how does the standard error change as n increases? Standard error becomes smaller. That's that inverse relationship. As one goes up, the other comes down, right? As n increases. So here, whether n increases or decreases, this relationship stays the same. Here, as n increases, standard error decreases. All right, for most farms in the Midwest, each 1/1000th of an acre produces on average 15,000 kernels of corn with a standard deviation of 2,000. Suppose 25 of these mini plots are randomly chosen on a typical day on a typical Midwestern farm. What is the probability that the mean number of kernels per plot will exceed 15,000? 16,000? 17,000? Okay, so let's think about what this is asking us. So imagine an acre, right? Split up into 1,000 tiny little plots, right? And so we'll call that, pretend that's 1/1000th. I know it doesn't look quite right, but pretend that is, right? And so in that little plot, this is the mean and this is the standard deviation for most farms. Suppose 25 of these mini plots are randomly chosen on a typical Midwestern farm. So what it's telling us is we don't know what this population, what that distribution looks like. We only know that on average, the mu is 15,000 and the standard deviation is 2,000. And we want to know what is the probability that we'll take a plot and look at how many kernels there are, and what's the probability that that mean number will exceed 15,000 or 16,000 or 17,000? Well, you can't actually just look at the population because we don't know if the population is normal, right? But we do know that the sampling distribution of the mean, that distribution approximates normal. So we'll use the SDOM. And although we can't draw the population because, it might look like this, it might look like this, it might look like this, right? We don't know what it looks like, but we do know what this looks like. This looks sort of like this, right? And we know what the mu is, mu sub x bar. We know that that's going to be 15,000 because we know it's the same as this. We also know the standard error of this, right? So standard error is standard deviation divided by the square root of n, and n is going to be 25, right? And so that is 2,000 divided by the square root of 25, right? So that is 2,000 divided by 5. It's 400. So we know that this is 400. And so we can say, what is the probability that the mean number of kernels per plot will exceed 15,000? So we take 25 plots from 25 of these mini plots, and we find the mean. What is the likelihood that that mean will exceed 15,000? Well, we could actually, let me color it a different color. So 15,000 is right here. What is that probability? The probability that that mean exceeds 15,000? So exceed 15K. So mean will exceed 15K. Well, we know that that's 50%, because we know that normal distributions are symmetrical, right? And that's 50%, right? Well, what about for 60,000, right? 16,000, sorry. So one thing that might be helpful to know is how many standard deviations away, right? And if you remember, you have to sort of think back to all that normal distribution stuff. We need to know where 16,000 is. So each jump is 400, right? So we need to know, sort of how many 400s away the 16,000 is, right? And in order to do that, we could actually just use z-score, right? So the z-score for 16K is 16K minus 15K over 400, right? So that's 1,000 over 400. So that's 2 point something. .5. And so we know that the z-score where 1600 is, 16,000, I'm sorry, is 2.5. So I'm running out of room, so I'm just going to delete that one. And you could look it up either in the back of your book, how much this area is, by using z-score of 2.5, given that this z-score is 0, right? You could look up that little area, and that's going to give us the probability that x bar exceeds 15K, and the probability that x bar exceeds 16K. The way that I'm going to do it is I'm not going to look it up in my book. I'm going to use the normal distribution functions in Excel. So norms dist, this gives me the area underneath the curve, underneath the normal curve for a particular z-score. So 2.5. Oh, actually, this gives me this area, right? So I need to do 1 minus this. And so that's 0.0062. So 0.0062. So the probability that x will exceed 15K is 50%, but the probability that x bar will exceed 16K is only 0.0062. So most of our x bars will be, below 16K, right?